Hello, so I'm Laura Lewis. Welcome to GCSE Chemistry, Ionic Bonding. I'm going to minimise myself, so I don't stare at me all the whole time. Okay, so this is suitable for the exam board. So OCR, EdXL, AQA, and other exam boards. Okay, so looking at the learning aims, you've got number 1, an overview of how ionic bonds are formed by the transfer of electrons. That's actually very important, it's a transfer of electrons. Number 2, understanding of how compounds are formed and naming conventions of new compounds, oxides, nitrates, sulfates, etc. Number 3, an explanation of the structure of an ionic compound as a lattice structure. Okay, well, a few things to get through there. So you may recall that an ion is a charged form of an atom. So an atom by itself is neutral, and an ion is the charged form of it. So there's lots of notation involved here. So we show the charge using a superscript. Plus, that means you're written at the top, or minus. It has to be at the top, it has to be a superscript. So e.g. Na+, that's a sodium ion, or Cl-, and they're both at the top, you notice there. So if an atom loses electrons, a positive ion is formed. So electrons themselves are negative. So if and atoms have equal numbers. This is in another video about atomic structure. If you've forgotten, you can go back and watch that. But atoms are neutral because protons are positive, electrons are negative, and they have equal numbers of each one. For example, the sodium atom there have 11 protons and 11 electrons. They can have different numbers of neutrons, but it's just in the bonding, it's just the electrons that make the bonds, but of course that the charge is affected by the number of protons it has and the number of electrons it has. So that brings us back. If an atom loses electrons, okay, loses some negativity, it becomes positive, and it's called a positive ion at that point. Okay, if it gains electrons, a negative ion is formed. Okay, so if it takes on extra negative charge, it becomes negative itself. So sodium, it's got 1 electron in its outer shell, loses an outer electron, okay, and it becomes Na+. So atoms, all atoms in the universe, want to be at the lowest energy state. And to be at the lowest energy state, they need to have a full outer shell, and they can do this by they're just losing some of the electrons from the outer shell, so just getting rid of it entirely, so all the other ones are full, the remaining shells are full, or they can gain them. So if you're an atom like sodium, you've got 1 electron in your outer shell, as you can see here, it's much easier to lose that 1 than to gain 7. So if you remember, full outer shell would be 8 electrons. So it's much easier for it to give it away, or to lose it, than it is to gain 7. The opposite is for chlorine. It's got 1, 2, 3, 4, 5, 6, 7. It's got 7 electrons in its outer shell. Much easier for it to gain 1 than it is for it to lose all 7 of those. Okay, so that really helps a lot in actually in all of science, is that everything wants to be at its lowest energy state. So protons, electrons, neutrons, pen. I will say write down pen. So write down with your pen. So worst examples, it helps remember. So sodium atom. Okay, we've got atom of sodium, atom. So remember, atom and ion are very different things. Atom, protons, 11, electrons, 11, neutrons, 12. Okay, the neutrons don't really get involved, so don't worry too much about that for this. So lose outer electron, protons stay the same, they sit in the nucleus, they don't get involved, it's only electrons getting involved in the bonding. So we've lost 1, so we're down to 10 electrons, and that becomes the sodium ion. So the sodium ion has 10 electrons, sodium atom has 11. Oxygen, okay, oxygen, 8, 8, and 8. Again, protons, neutrons don't do anything, they just sit there. So this is a little bit different. So 1, 2, 3, 4, 5, 6, it's got 6, and the way of writing that is 2, 6. Okay, so that's the correct way of writing out, I think it's called the configuration of electrons is 2, 6. So to get a 4 outer shell actually needs 2. To lose 6 is harder than to gain 2. So it actually loses 2 electrons. It gains 2. Sorry, it gains 2. So it's got 1, 2, 3, 4, 5, 6. It gains 2 electrons rather than losing 6. It gains 2. So it forms a O2 minus ion. If you look, it's gone from 8 to 10. Okay, so it's got 2 more electrons. It's now an oxide ion. So as we go through, the names of these things sometimes change. Is that metals keep their names. Okay, so sodium is a metal, so it keeps its name as sodium. If it's a non-metal, it changes its name. Oxygen goes to oxide ion. Okay, so they change their name. It's just a convention you get used to. Metals stay the same. Iron will be iron ion. I always like saying iron ion. Magnesium ion. Okay, so oxygen oxide ion. It's chlorine. If we go back a bit, chlorine chloride. Okay, chlorine chloride. So yep, again sodium stayed the same. Okay, so a little bit of interest here about the sizes of these things. Okay, so we always represent the nucleus to be quite big, but in reality it's really small. Okay, so sometimes you talk about bond lengths and things, like the length of the bonds. They're so small, like these things, we can't see them with our eyes. So yeah, chemistry uses nanometers to quote distances at an atomic level. 1 nanometer is 1 times 10 to the minus 10. Okay, the radius of the atom is about 0.1 nanometers there. Sorry, I just want to put my screen back up again. Sorry, I lost the screen. Compare this to the approximate radius of the nucleus, which is 1 times 10 to the minus 14. So if it was a sort of a big sports stadium, the nucleus is tiny there, and the electrons are as big as sort of the stadium seats. So we talk about forming ions and things. They are very far away, okay, from the nucleus. If you want to have read that slide, to put it in, quite a lot of interest there. You wouldn't have to remember these numbers at GCSE, okay, just a bit of interest I put in there for you to see that the size of these things. So let's have a look at the patterns. Let's go back to what you will be asked at GCSE. So we look at the periodic table. You may have been asked to colour this in class. I always got students to colour it in class with the metals, non-metals, all that sort of thing. First year of year 7, come to see that. And you find out now it actually becomes more important to know these things. It wasn't a waste of time. No one's ever done that. Okay. So remember, groups go down. These are a group, so like a kind of family. Okay, group 1. Okay, so group 1 very easily have 1 electron in their outer shell. You probably get no prize for guessing that group 2 have 2 electrons in their outer shell. These are transition elements. We'll talk about those in a moment. Okay, these are group 3, 3 electrons in their outer shell. Okay, these are featured in a different video. These are the covalent compounds. So they're in a different video. They don't form ionic bonds. So things that are blotted out by this nice sort of lilac colour form ionic bonds or the more complex bonds. Okay, these ones are all featured here and over here. They can form ionic bonds. Okay, that's a good thing. So that's why you do the colouring of the periodic table, because actually these things later on in GCSE we're doing now, they form different bonds. Okay. Group 3, group 4 this is, but we'll talk about group 4 in the video. But yeah, there's whole branches of chemistry devoted to group 4, okay, whole fields, organic chemistry devoted to it. Okay. This is actually group 5, okay, group 6, group 7, sometimes there's group 8, sometimes 0. We'll go through why they've got minuses and pluses above them in a moment. Okay, so group 1, okay, they've got 1 electron, outer shell, easier to lose it. So they'll form a +1 ion. Okay, this is what these numbers mean. It means the ions are from hydrogen, lithium, sodium, potassium, rubidium, cesium, francium will all form +1s. That's why they're in a group. They all behave in a similar way. Okay, they all form a +1 ion. Group 2, they're 2 electrons. They will lose 2 rather than gain 6. It's easier. So they'll be written as +2, so Mg plus 2, calcium plus 2, beryllium plus 2, strontium. So I like that name, that element. Strontium plus 2, barium, looks like barium, it's barium plus 2, and radium, my favourite element, plus 2. I wonder what it's very radio. These things down here are very radioactive. They do have their uses, but they're very interesting. Okay, so watch videos on the radiation to find out. Group 3, again, they'll rather lose 3 than gain 5. Okay, so aluminium, gallium. Okay, these ones are a little bit anomalous, but they can form ionic bonds. So zinc, silver, so Ag silver, argent in French. Look at Ag. Cadmium, they can form. Like zinc, cadmium plus 2. They're all metals. Plus 1. They can form. So up to this point, these are all metals. Up to this point. Then group 4. Okay, yeah, they don't form ionic bonds. They form covalent bonds. So that's in the covalent bond video. -3, so group 5. Right, so we're getting to group. Right, so at this point, they'd rather gain 3 electrons than lose 5. More sensible. So nitrogen, phosphorus, they gain 3. They're going to form an ionic bond. Okay, so they would form N-3 ion, P-3 ion. Oxygen we saw earlier, -2. It's easier for them to gain 2 than to lose 6. Sulfur and selenium, -2. These are very reactive. Fluorine's the most reactive element in the whole periodic table, fluorine. So fluorine will just grab electrons off anything. Okay, so it is very reactive, and it just needs 1 to complete. So fluorine, chlorine, chlorine's quite dangerous. Bromine, iodine, they're all fairly dangerous elements on this on that group. Group 7, also known as the halogens. Halogen means salt maker because they make salts. And I don't mean just the salt you put in your chips, but that is included in salt. So sodium chloride, you got fluoride, it could be called sodium fluoride. You could get magnesium bromide. Okay, so if you notice, well, they're changing their names, aren't they? Again, group 0, probably you know them, known as noble gases. They don't react with anything. I've obviously left them on here because it's important to know about these. They don't react with anything. Noble gases. They have full orbitals. They're very stable. They don't really get involved in anything. Okay, so noble gases. She could be asked what the electron shells are full. They don't need to be involved in anything. Okay, examples of ionic compounds. Okay, so the compound itself must be electrically neutral. Okay, because that's the lowest energy state that something can be. They don't want to have a charge. So the compound, yeah, must be formed of equal positive and negative charges. Yeah, nice and simple. So nothing really more difficult than that. So magnesium, oxygen. Okay, so magnesium. Remember, group 1. Okay. Oh no. Sorry. Oh wait, no. Magnesium group 2. So I thought I read sodium, but magnesium. So let's go. You can always have a periodic table. Goes back and check because it's obviously, even if you're used to it, you can make mistakes. So magnesium +2. Magnesium 282. You can see there as well. It's 2. Magnesium 2. Oxygen 6. Aha. This is good. Actually, this is very good. I always see the ionic compounds as a bit of a business transaction. So one of them wants to sell their electrons, the other one wants to buy. They make a nice business deal. So magnesium, I want to sell my 2 electrons. Oxygen, I want to buy your 2. Okay, so magnesium will happily give its electrons to oxygen. Okay, so you just need 1 magnesium and 1 oxygen. Okay, so the 2 will be taken by the empty spaces in the oxygen, and everyone's happy. Okay, you've got magnesium oxide, is how you'd say that. Magnesium oxide. So it's an oxide ion. So it's a little bit more involved. Calcium. Calcium is a very big atom. It's in our bones. It's got a familiar element, calcium. 2A82. Okay, it's 2. It's group 2 as well, but like magnesium, same family. Chlorine. Think, why is there 2? Why is there 2 chlorines now? Right, so calcium wants to sell. Okay, think of it as wants to sell 2. It wants to get rid of 2. Chlorine, just by itself, wants 1. Okay, but if calcium gives 1 electron to chlorine, it's still got 1 left. So why not give it to another chlorine? That's what it does. because that means everyone's happy again. So calcium gives one electron to one chlorine and one to another. So you've got one calcium in the formula, calcium, Cl2, calcium chloride. Okay, calcium chloride. So the number doesn't really change the naming of it. Okay, so here you have magnesium oxide with one oxygen, calcium chloride. Okay, it does sometimes change the name, but not on that occasion. So now they're all happy because this forms a 2+ ion, losing 2 minus minus. So 2 plus minus minus, overall 0. Everyone is happy. Okay, let's have some more examples. The best way of knowing this is just lots of examples, really. You'll get used to it. The formula of ionic compounds, yeah, it's like a balancing act. The positive charges must equal negative. My animation is working today. So sodium 1+ balances 1 chlorine, sodium chloride. This is what you put on chips or in other things. I mainly put it on chips, so it's salt. Okay, what you put on chips. Okay, a little bit more complicated. Aluminium 3+ wants to react with oxygen. Okay, I've got electrons to sell. Oxygen like to so we've got a buy and sell thing. Okay, not balanced, is it still? So sometimes it's not straightforward there because these are different charges, but it doesn't mean that they can't react. Okay, so you think, how does that work? This can work. Okay, so you can actually have 2 aluminiums. This is the bit that students find the hardest in whole chemistry, I think. 2 aluminiums and 6 overall charge -6, but 3 oxygens. So over here it's +6. Over here, if you add them together, -6. Both charges balance, okay? And you may have gotten to balancing equations yet. This is what balancing equations really means, balancing of charges, okay? Yeah, it's something to get used to. Sometimes even people that sort of teach us a lot, you have to write it out in pencil and see what works. Aluminium oxide, okay? Okay, you've got the ide. Sodium chloride. Okay, so often ionic compounds will form structures called lattices. Not the same as lattice that you may find in a bakery. Okay, but it's kind of based on the same thing of things crossing over. Okay, intertwining. Okay, a lattice. So, and often lattices are seen as crystals. Okay, so sodium chloride actually forms a beautiful crystal. You probably never noticed it. You've seen it under a microscope. But if you just go right back to the slide at the beginning. Okay, I'm sorry about that noise, the computer. That is a crystal of sodium chloride, a common table salt. If left to grow, it will form a beautiful cubic, perfectly cube crystal. Let's go back to see the arrangement there. Okay, so you've got sodium ions and chloride, remember, ions embedded, okay, together. Okay, all bonded together and in a regular pattern. So it goes chlorine, sodium, chlorine, sodium, chlorine, sodium. Okay, like that regular pattern. That's what it means. So that sodium, chlorine, sodium, chlorine, and it goes like they all sort of want to touch. It's a bit like a puzzle, isn't it? You might find they have to line all the puzzles up together. Have very strong bonds between them. The chlorine and the sodium so happily bonded. They don't want to be separated. Okay, they've got very high melting points. Okay. So ionic compounds do not conduct electricity when solid. Okay, so table salt would not conduct electricity, it's not good to use in a circuit, not when it's solid. Okay, so for substances to conduct electricity in general, 2 conditions must be met. A substance must contain charged particles. Well, it does, isn't it? Must be free to move. They're not free. Okay, so they're not when they're solid like this. So I jumped a slide. When they're solid, they're not free to move. So why can molten dissolved conduct electricity? So if you melt it down, the ions all kind of are freer to move. They're not quite as joined. So if you melt it, they're a liquid. Remember, liquid can slide over each other. They're freer to move. Okay, so molten salt, molten sodium chloride can actually conduct electricity. The same kind of thing happens when you dissolve salt in water. The sodium and chloride ions disperse in the water, so they actually spread themselves out in the water. and conduct electricity. This is why people say water conducts electricity. Pure water doesn't. Pure water is very, very rare. So you always have to assume it's got some salts dissolved in it. Okay, it's always got something dissolved in it. So sodium chloride dissolved in water conducts electricity. Okay, just go over a few things. So ionic bonds are formed by the transfer of electrons. I've talked about a few times. How compounds are formed, naming conventions, new compounds. So oxygen oxide, if it was bonded with nitrogen, it'd be a nitrate. Bonded with sulfur, it'd be a sulfate. We also saw chloride there. Okay, so naming conventions, you have to get used to. An explanation of structure of ionic compound as a lattice structure. Okay, so that was the last thing, was a lattice structure. Okay, so thank you for joining that class. I will be seeing you in the next class. Thank you. Goodbye.